All right. It might be a bit noisy in the background today because we're recording at school. We'll see how we go. There might be bells. There might be announcements. We'll see what happens. Okay, today we're going to talk about how we can use the derivative and the double derivative to work out what's going on in a graph. So we need to know a few little things. So at a maximum turning point, we know it's a stationary point, so we know that the derivative function is equal to 0 at that point. Okay, but what's going on with the double derivative? Now the double derivative could be 0 or it could be less than 0. It could be a negative number. So it could be less than or equal to 0 at the maximum turning point. So the way I picture this is if the double derivative is less than 0, then the curve is concave down, and if dy dx equals 0 at that point, then we've got a local maximum turning point. Okay, same with the minimum turning point. If the minimum turning point is 0, dy dx is 0 at that for a minimum turning point. If it is greater than or equal to 0, well, concave up. Okay, concave up. So if you think more than 0, concave up, less than 0, concave down. Okay, so it might be a bit confusing when you think we get less than 0, but you get a maximum turning point. That's because less than 0 means concave down. Okay, stationary points of inflection. Stationary points of inflection could be when the derivative is 0 and dy dx is 0. Now, so if you get 0 and 0 for both, I don't think that's enough information to be able to tell whether it's a maximum turning point, minimum turning point, or stationary point of inflection. You have to check what's going on either side to actually know of the point whether it's one of those things. Because if you have, for example, well, y equals x cubed, so y equals x cubed at x equals 0, we know that dy dx is going to be 0 at x equals 0, and the double derivative is going to be 0 at x equals 0. So, and we know this one's a stationary point of inflection.
For year 7 to year 9, please rotate activities now. Thank you.
I wonder if I'll be bothered to cut out that announcement. We'll wait and see. So we've got this case, but if we want a minimum turning point, all we'll have to do is go x to the 4, and we've got 0 for both cases. Or if I had y equals, if I just flip that upside down, negative x to the 4, then I should have that case there. So each case I've got the derivative equal to 0, double derivative equal to 0, but I either have a maximum, minimum, or stationary point of inflection. So if you got 0 for the double derivative and the derivative function, you do a little bit more searching to work out what it is. Okay, point of inflection. You get points of inflection that aren't stationary. So this is just where you have a change in concavity. So if you're going from a maximum to a minimum, there's a point in here somewhere that's a point of inflection, change in concavity from maximum to concave down to concave up. Okay, so that's when this is not equal to 0, but dy dx, I forgot my double derivative, d squared y squared on the bottom there. Yeah, so when the double derivative equals to 0, but the derivative isn't equal to 0, indicates you've got a point of inflection that's not stationary. Okay, let's have a go at one and see what happens. Okay, let's get rid of this. Let's see how we go. Let's try f of x is equal to x cubed plus 4x squared plus 4x. Okay. What can we do with this? What do we know so far? Let's try and work out a few things. Well, we know the y-intercept, don't we? So let's go f of naught. What's that going to equal? Naught, 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 gives me naught. Okay. We know that already. So we've got 0, 0, which gives us an x-intercept as well. So that's nice. What else do we know? Well, let's try and find the other x-intercepts if there are any. We're going to go f of x equals x squared plus 4x plus 4. We can factorize this. X plus 2 all squared. Therefore, negative 2, 0 is x int, y int up here. So we've got the intercepts, okay? And because this is a squared function, we might already know that this one is going to be a turning point. So a turning point on the x-axis. So let's rub this out and just summarize this information up the top. Let's put it in red. We know negative 2, 0 is a point, and we know that's a turning point as well, just because we know a few different things about graphs, and 0, 0 as well. Okay, let's take a derivative and find out where those first stationary points are. Okay, so f prime of x, what's that equal to? We've got 3x squared plus 8x plus 4. All right, let's factorize that one. We could group it if we wanted to, otherwise we can use the cross method. Let's use the cross method. 3, 1, 2, and 2. I get 6 plus 2 is 8. That works for me, so I've got 3x plus 2 and x plus 2. Okay, so if I set this equal to 0, it tells me where my stationary points are going to be. So I've got x equals negative 2/3 and x equals negative 2. Okay, so that's great. That's the x points. Where my stationary points are, I'm going to have to sub them back into the original function up here to work out what the y points are. So negative 2/3 and negative 2. Don't forget those. Okay, negative 2/3. Yeah. So I know, I should have written them up here first, that would have been smart. Turning points, negative 2/3, so they're the intercepts. I don't know why I'm doing it like this. That's rubbish. Doesn't matter. Okay, maybe set notation. That's better. Negative 2/3 and something. And negative 2 and something else. Okay, my stationary point set. Okay, so I've already factorized this top one to be f of x equals x plus 2 all squared. So that might be easier to put my numbers into. So let's go with that. Negative 2/3. Negative 2/3 plus 2. So that's 6 on 3. What have I got now? I've got 4 on 3 times that is negative 8 on 9. Let's see if I got that last time. Did I get that last time? Not even close to that last time. Oh, squared. Bugger. Alright, let's try again. Negative 2/3 times 4/3 squared. What do I get? I get negative 2/3. You've got to do all the steps, otherwise you make silly mistakes. Well, I do. I make silly mistakes. Okay, so what have I got? I've got negative 32 on 27, which is not the answer I got last time either, but I think that might have a better chance of being right. Let's go with it for now. Negative 32 on 27. All right. Someone else can check it for me later. You're probably screaming at me because of the mistakes I make, which is fine. That's a good thing. What have I got? X bracket x plus 2 squared. Let's put in negative 2. Surely I can't get this wrong. Negative 2 plus 2 squared. This is just naught, isn't it? Naught. Okay. So, we already knew this was a turning point at negative 2 naught. So that's what we expected to get. Well, that's handy at least. At least that makes sense with what we had before. Now function. Cool. All right, let's do double derivative. Double derivative. I've forgotten what the actual derivative was now. Okay, so the double derivative is going to be, I'll take this twice. Get 3x squared, then 6x. Get 8x, so plus 8. So the double derivative is that one. 6x plus 8. Okay, so let's find out when the double derivative. Let's find the double derivative at these points, and let's see if they say whether it's maximum or minimum. So let's go double derivative at negative 2/3. Okay. Let's see what we get. We get 6 times negative 2/3 plus 8 equals, what do I get? I get negative 12/3 plus 24/3, which is 12/3. That's a positive number. So I've got how should I write this down? I don't really want to write it down as a set of coordinates because it's not really a set of coordinates. I just want to know that this is greater than 0. So at this point, greater than 0 means concave up. So that means it could be a local minimum. Well, it should be a local minimum at that point. So at negative 2/3, I've got a local minimum. Let's see what I get at negative 2. So, let's write it in. We'll just write min. That's how I'll remember. Okay. And negative 2. Stick that in. What do we get? 6 times negative 2 plus 8. What's that equal to? That's, these days, it's negative 12 plus 8, which is negative 4, which is less than 0, which means concave down, which is a max. Okay, so we've got a maximum turning point there, minimum turning point there. We could also try and find if there's any points of inflection. So let's set this equal to naught. Find out what our x is. Well, between the max and the min, there has to be a point of inflection somewhere. So I get x equals negative 8 on 6, which is negative 4/3. So at x equals 4/3, we should have a point of inflection. So let's stick negative 4/3 back into the original function. And we get, what do we get here? Negative 4/3 plus 2, which is 6/3. I've got to square it. Don't forget to square it. What's that? 2/3 squared, so negative 4/3, 4 on 9 equals negative 16 on 27. Okay, negative 16 on 27. There we go. So we've got a point of inflection. This is a coordinate now. I can use this. Negative 4/3, negative 16 on 27. So we should be able to give that a quick graph, work out what that looks like. Let's just do it really quick. This is going to be a rubbish graph, but that's okay. Here we go. We've got x, we've got y. So at negative 2, but here's my negative 2. So negative 2, 0. Let's write it as a coordinate. That's what we're supposed to do. And it's going to turn around. It's going to go back through 0, 0. Back through 0, 0. Minimum turning point should be negative 2/3, negative 3 on 2 on 27. And we should have a point of inflection here at neg 4/3, neg 16 on 27. And there we go, got all those points labelled. All right, that's it for this video. See you next time.